Hello, thank you all for joining us today. I'm Katie Austin, Senior Project Manager for New Reactors at the Nuclear Energy Institute. I'm excited to be moderating today's discussion on the Versatile Test Reactor and its essential role in expanding the United States research capabilities and supporting the next generation of nuclear power to help achieve clean energy goals. Before we get started, I'll cover a few housekeeping items. First, all attendees are muted. Throughout the discussion, please send us your questions using the question box in GoToWebinar. We'll pose questions from the audience to our panelists later on. The webinar is being recorded and will be available on the VTR website at inl.gov/VTR. I'll kick off our discussion today with some short remarks. Then Kamal Pasamemitolu, Executive Director of the VTR project, will provide us with an update on the VTR. Finally, we'll have a discussion with our panel, which includes participants with diverse expertise in the nuclear energy sector. I'll introduce them a bit later. Let's get started. There's a recognition of the need to transition our energy sources and ultimately decarbonize the entire economy. We see that in goals ranging from the carbon-free commitments utilities have made to recent actions at all levels of government. For example, in January, the new administration set a goal for the United States to achieve net zero emissions economy-wide by no later than 2050. Then, in April, the administration set a goal for the United States to achieve a 50 to 52% reduction from 2005 levels in economy-wide net greenhouse gas pollution in 2030. With the longer-term goal of decarbonizing the entire economy, it's important we develop and deploy technologies that help to decarbonize sectors that include industry and transportation. Nuclear technologies and the carbon-free heat they can provide are crucial to achieving this goal and reducing dependence on fossil fuels. The breadth and scale of the challenge ahead of us prove how important it is that nuclear technologies are part of the clean energy solution. That's why the projects underway now are so important, including those led by Oklo, NuScale, TerraPower, X-Energy, and many other advanced reactor companies, and the Versatile Test Reactor. The VTR will expand on the world-class scientific research and development capabilities that exist in the United States today. It will perform tests and experiments for both advanced and existing technologies that just aren't possible with today's infrastructure. In fact, the only fast neutron testing capability currently available in the world today is in Russia. This presents challenges to US reactor developers who need this type of research and testing capability. VTR will help scientists and engineers create even safer, longer lasting, and more efficient fuels, materials, sensors, and instrumentation. These advancements are important to not only decarbonizing our electricity grid, but our entire economy. The VTR has a crucial role to play in our energy transition. It will also help reestablish the United States as a global leader in clean energy and nuclear technologies. With that, I'll turn it over to Kamal to share an update on the VTR program.
Thank you, Katie, and thank you everyone for attending the webinar today. It's my pleasure to kick off the panel session with some introductory comments, primarily to give you an update on where the VTR project, what it is, where it is, and what we plan to do in the near future. Next slide, please. What VTR is in the traditional sense, it is a test reactor. Its objective is to generate neutrons that can be used for testing fuels, materials, instruments, sensors, or any other elements that need to be exposed to a neutron flux. It's just like an advanced test reactor, except VTR is being designed to produce neutrons at high energy, at very high fluxes. The design, it is a full-type sodium-cooled reactor. It's based on General Electric Hitachi's long investments on the PRISM A reactor with the necessary modifications to adapt it to test reactor conditions. In that respect, we have basically modified the core considerably to make sure that we meet the experimental requirements by all the stakeholders. What you see in the cross section is some hexagons, and those are the fuel assemblies in the core. The core size is 300 megawatt thermal, so it's fairly small. We do use plutonium-bearing fuel to achieve the high fluxes that we need for this experimental environment. The objective in designing the core was to really minimize the core size while making sure that we have a very high flux, neutron flux at high energies over the experimental volumes that are desired for all the experiments that we want to conduct. That's why the plutonium is used in the fuel to maximize the neutron flux. If you look at that cross section over there at the hexagons, the magenta colors there are 6 of those. Those are the permanent test locations in the core that for experiments where we need to use instruments and sensors in the experiment where they need to be connected to the upper head. We have permanent test locations. There are 6 of those. One of them will likely be used for a rapid irradiation, which is really being able to insert test specimens in and out while the reactor is still operating. The other 5 will likely be used for some what we refer to as cartridge loops, where we can introduce loops into the core where different coolants are circulating, such as lead bismuth, gas, or molten salt. In addition, for practical purposes, we can use any one of those fuel assemblies, replace them with a test assembly. And for example, the lime green color ones are some examples of where they can be, but in theory, we can do that with any of the test assemblies as long as we can balance the neutronics environment. The objective is to be able to run at least 10 experiments concurrently at any given time. The analysis so far and the design evaluations indicate that we can do much more than that if necessary. Next slide, please. Where we are with respect to the project started officially in 2018. In February of 2019, the mission need was approved by the Department of Energy. More recently, in September of 2020, we have achieved critical decision 1, which is basically selection of the alternatives and that narrowed the option down to a pool-type sodium-cooled reactor, approval of the conceptual design, and cost and schedule range. Currently, we are at the final phases of completing the environmental impact statement. We have done the public comment period. We are addressing those comments right now with the objective of having a record of decision to proceed with VTR and the location of VTR in summer of 2021. The preferred location for VTR is the Idaho National Laboratory, but Oak Ridge National Laboratory is also being looked at as an alternative. So from there, the next big milestone is going to be a combined critical decision 2 and 3, which will be the completion of the engineering design, baselining the project, and starting the construction. How quickly we get there depends on the yearly appropriations. At critical decision 1, we were targeting 2023 as achieving critical decision 2 and 3. However, we are also looking at alternative scenarios with where the yearly appropriations are spread over multiple years. to make it affordable. So we are looking at a range of 2023 to 2026 for critical decision 2 and 2026 to 2032 for basically getting the reactor critical. Next slide, please. Currently, we have 10 major industry partners in the project. Those are the ones who are continuously helping up. It doesn't count the temporary consulting services and all that. 18 universities, primarily focusing on experimental capability development for the VTR, and 6 national laboratories. I'm happy to state that we are very close to being able to sign the contract for the engineering, design, and construction phase of the project very soon, with the team that's led by Bechtel National Incorporated, but they do have their partners TerraPower and GE as partners to that team. On the international front, we do have active collaborations with France and Japan. Next slide, please. Now, as Katie indicated, I think we are at a transition phase, not only in the United States, but globally, into a different energy economy. A big driver for it, of course, the need for clean energy, but equally as important is an equitable energy, affordable energy for a world that's quickly approaching 10 billion people. And I do believe that nuclear energy will play a very important role in that next phase of our energy landscape. However, I do believe that the way we deploy nuclear energy is going to be slightly different than what we did until now. I think one size fits all is not going to be able to get us there. It's going to require different types of designs, both in size and in technology, that are tailored to regional needs, both in the United States as well as globally. I believe that to get there, we need to start demonstrating the reactors that are ready to be demonstrated as quickly as possible, with potential future upgrades between demonstration and commercialization phase. But at the same time, we should also support the ideas, the designs that are not quite ready for demonstration, but have a potential for having a serious impact on the future of energy landscape, both nationally and globally. That's one of our US policies in transitioning to a clean energy economy, as Katie indicated, by almost 100% by 2050. Another objective, of course, in that future where nuclear energy is playing an important role globally, is going to be achieving and sustaining the US leadership in that technology, just like we did for many decades for light water reactors. Next slide, please. So that is important, but US leadership has to include all the different sectors in this effort. Certainly, we need to have a very strong competitive commercial entities playing in the global market we need to support those efforts with continuous innovation. That's where the R&D infrastructure that underpins all those commercial efforts come into play. We should be able to enable exports of the US reactors and associated services, and tailor those again to the regional needs with the necessary modifications. The US leadership is not all about just the economic benefits of being the provider of this technology to the world. Certainly, it has a national security element, and our influence on global safety and security policies is very important. And our capability of adapting to changing market needs and geopolitical landscape as we move forward. These are reactors are multi-decade investments, and our ability to adapt those to changing environments is very critical. And it's not on the slide, but our ability to bring in the next generation of workforce, the human resources, the new nuclear scientists and engineers is very important for us to regain and sustain the leadership. And in that respect, VTR will also be a critical part of the US nuclear energy research and development infrastructure. Next slide, please. Finally, I want to make a few comments about public-private partnership. For US to achieve its, in general, its energy goals, energy objectives, but in particular the nuclear energy, national nuclear energy objectives, we must certainly have a very strong commercial sector. And that means we need to support the cost-share demonstration reactors as those designs are ready for demonstration. However, that by itself is not enough in the long term. We need to complement that with a very strong R&D infrastructure that can support both the pre and post demonstration phases of those reactors. I do believe that to achieve those goals, we need a strong public-private partnership. However, I believe trying to define a public-private partnership for each project and for each level of work that we need to do to get to the end objective is not the right way to look at it. I think we have to look at the public-private partnership at the level of national goals and properly define the role of each sector, both the public sector and the private sector, where they can play their traditional missions. Along those lines, I'm happy to announce that VTR and Natrium teams are exploring a collaborative framework where we can utilize the resources in an optimum fashion while trying to achieve both missions, the demonstration mission as well as the long-term R&D mission. Given the fact that the designs are fairly similar, the teams working on that are roughly the same. I think that will be a tremendous benefit if you can achieve those in a collaborative fashion. And from our end, and that goes back to my slide that I showed the range of the CD2, CD3, as well as CD4 startup. We are looking at reviewing our schedule vis-a-vis the Natrium schedule that's fixed, where we can take the maximum advantage of the design synergies between the two projects. And with that, I'll turn it over to Katie.
Thank you, Kamal. That presentation is a great segue into the conversation that we'll be having with our panelists. So I'll start by introducing our panelists. And while I do that, just a reminder to folks that we will be doing a Q&A, taking some of the audience questions towards the end of today's webinar. So remember to put your questions in the question box on GoToWebinar. So today we have Eric Loewen, Chief Consulting Engineer with GE Hitachi Nuclear Energy, Caroline Cochran, Co-founder and Chief Operating Officer for Oklo Inc., Niko McMurray, Nuclear Program Director at ClearPath, Tom Nixon, Senior Project Manager with Bechtel Corporation, and Randy Stark, Director of Fuels and High-Level Waste and Chemistry at the Electric Power Research Institute. Thank you all for joining us today. I'll kick off our conversation with a question for each of you, and I'll pick on Eric first. Eric, Kamal gave a good update on the status of VTR. Would you please describe how VTR will benefit from the past work, such as the Fast Flux Test Facility and GE's PRISM design, and how it will be different than the sodium-cooled fast reactor that TerraPower and its partners are going to build?
Sure, Katie, thank you. The VTR is leveraging two great programs we had in this country, or really three: experimental breeder reactor number 2, the fast flux test facility, and the advanced liquid metal reactor program that was started in this nation after Clinch River was canceled. So it ran from about 1984 to 1994. And in that, 9 US industries or 9 US companies designed and put in front of the Nuclear Regulatory Commission the design of what we call PRISM, Power Reactor Innovative Small Modular, or Power Reactor Inherently Safe Module. Depends on which side of the legal debate you want to be on. And that design went through the Nuclear Regulatory Commission. They issued a preliminary safety evaluation in 1994. Sorry, we're being attacked by the bulldog. And in that context, so in that context, we leverage all those to build the Versatile Test Reactor. So it's a great team that I have the opportunity to lead. I'm going to relinquish my leadership to Tom when they sign that construction contract here very shortly, and then I'll be more into the supportive role. Now, how it differs from Natrium is a commercial reactor. They want to make electricity. They have some innovative ways of how they do that with salt storage, leveraging what the solar industry does. In that case, the VTR, so it can be licensed, or not licensed, regulated and approved by the Department of Energy, they are allowed to do that if they don't make electricity. So the picture that Kamal showed of the road that you could drive up to the VTR, you saw in the back 10 different stacks sticking up in the air. Those will reject the fission heat into the atmosphere, and that allows the DOE. So Natrium will be licensed by NRC. The VTR will be licensed by the DOE. So that's, I'll yield it back to you, Katie.
All right, thank you. And so you mentioned a handoff to Tom, so I will go ahead and call on Tom next. You've worked on the new reactors being built in Georgia at the Vogtle plant, and now you're working on the VTR project. What sort of lessons learned and experience are being transferred to the VTR project, and how does this experience benefit the nuclear workforce?
All right, well, thank you, Katie. First, I want to acknowledge the amazing people down at Vogtle, both past and the present. They've been doing some fantastic things down there, and I was fortunate to work with some of the best in the industry. But there were a lot of lessons learned in many different areas of the project. One of them being that we need to have the design complete before we actually start into construction. As some of you may know, the AP1000 is something that's been used across the globe, and it's a standardized type design. But when you come to the US, there's some certainties that you need to use to certain designs that need to be modified, like redundancy and electrical work. That forces you to have more cable tray, more cable runs, which means you're going to have more penetrations in the walls, and you end up redesigning the plant in some respects. So there's some big things there that we want to be able to take and learn and carry across the VTR, which we will. The other is the undergrounds, the way you kind of build the plant. At Vogtle, they started off with the key pieces of the plant and not really focused on some of the underground pieces like grounding and some of the major piping that's needed. So we want to do that first and kind of bring that up as a whole, as it meets the schedule requirements of the project. So we want to maximize our potentials and get the efficiencies right there. So we learned some of those. The other thing is new work like steel composite designs that I know Hitachi has been looking at and we've used in the past. And we actually used a lot of that down at Vogtle, and it proved quite well when you plan it out properly. We want to take that and use that as extensively as we can with VTR. And then we also want to look at tolerance buildups. If you're building a tall building, you have a limited tolerance at the top when you're building all the way up, but sometimes those get used up as you start building. And so that was a problem down at Vogel. We needed to figure out how to bring it back around and align it to be as vertical as possible. We also are going to be using virtual design and construction. We did not use that at Vogel, but that's a new approach where we're going to be applying that in full earnest on the VTR project. And then we want to start throwing in some of our EPC tools that we did not see so prevalently down there. So one of the things that I learned down there, working on all these different sites over the years and over my career, is that we have a lot of construction professionals that like to see the work done. And the best way to get there is to get rid of some of these hurdles out, like get the lessons learned, get that established in front of people, and make sure that they have the tools, because there's really one mission when you get to the job site, and that is enable the craft to turn the nut, weld the pipe, align the pipe, and without delay. That's where the biggest things are. And so we saw a lot of that there, and we'll be pulling that experience. And speaking of the craft, all that experience, if we start to lose them because we don't have the kind of things like Kamal was talking about, making sure that we have the future, after Vogel is done, we don't have another project, we're going to lose a lot of that experience. That craft goes away, and they're the only ones right now in the country that can do it as well as they can. And so we need the Natriums, we need the VTRs, we need that kind of stuff to be able to maintain that, not just in the craft side, but also in the field, not manual. So it's prevalent that we keep moving forward on it. Back to you.
Thank you. Next, I'll turn to Caroline. Oklo has an application under review at the NRC for your Aurora powerhouse, a 1.5 megawatt electric fast reactor that will be built in the next few years at Idaho National Lab. Since you will be building your reactor before VTR is up and running, how will VTR help Oklo?
Thank you, Katie. And I just wanted to alert people that there may be some lag. I apologize for that. Maybe my video and audio will be a little unsynced. So I'll try to speak slowly and clearly in case that's the case for you all. Yes, I think a lot of people might think, Oklo, was a first mover. We were the first non-LWR to begin paid meetings with the NRC in 2016, and we do currently have a combined license application for construction and operation of a nuclear plant, including a fast reactor, for the next few years. So I think people might wonder why we would advocate for this. I have a couple hats that I'd like to answer this question. Both as Oklo and as Oklo chairs, well, Jacob DeWitt from Oklo chairs the Fast Reactor Working Group. But what I'd say first is, Oklo is basically was able to do that, and we really believe that we're able to do that based on standing on the shoulders of giants that came before, right? We were able to utilize data from an experimental breeder reactor from that operated from the 60s straight through to the 90s. A lot of people don't realize 30 years worth of operation and data that was able to be gleaned. And that was needed in order to submit the application, we believe. But we need current assets to do that for decades to come. And I think that's one really important piece of the VTR. I would also say, the Fast Reactor Working Group, of which there are approximately 15 members with all different coolant types and all different fuel types. Lead, salt, gas, and sodium, including the coolant types and all different types of fuel types, are all interested in having such an asset in the United States. So we, through the Fast Reactor Working Group, have been requesting and advocating for this asset for some years now. And then lastly, what I'd say is just having an asset like this can also help other technologies in terms of materials, or even us. One thing we're excited about is being able to use it for materials testing and other types of testing that may not be readily apparent, but that can really advance the next generations of designs, and even including fusion, right? I think the broad energy spectrum and being able to put materials in that environment could even benefit fusion energy. So we see the benefits as broad, and even though we expect to have one and maybe several reactors up before VTR is up and running, that does not in any way in our mind decrease its value as an asset to the nation or to the future of nuclear power.
Great, thank you, Caroline. So speaking of the benefits to the various nuclear technologies, Randy, the VTR is a fast reactor, which means it's fairly different than the reactors that are currently operating in the US. And even though it's different, would you discuss how the experimental facilities at VTR will be able to support the continued operation of the existing fleet?
Yeah, thanks, Katie. Thanks for the question. One of the key strategies for a clean energy future is to make sure that the existing operating light water reactors continue to operate reliably and affordably into the future. We still have 90 plus reactors in the US, light water reactors, and several hundred additional light water reactors worldwide that are operating today. So to ensure that they continue to operate reliably and affordably, there's no question we need experimental testing facilities. There's still gaps that we're trying to understand in terms of structural materials. From a structural materials standpoint, irradiated data is needed to support long-term operation. Plants are going now beyond 60, maybe someday beyond 80, beyond 100 years. We need to understand how radiation impacts materials in light water reactors. From a fuel standpoint, we're now introducing advances in fuels, fuel claddings. We're also introducing changes to the way in which we operate our fuels, flexibly going to higher burnups, maybe higher enrichments. Irradiated data is needed to address those questions that come from the advances in these technologies and new operating conditions. So the question is, can VTR support this? The short answer is yes. The LWR, the light water reactor research has leveraged all types of reactors over many decades, including fast reactors. Fast reactors do have the advantage of accumulating high levels of fluence in a short period of time, which can be beneficial when we want to understand how radiation damage can impact materials. There are differences, as you mentioned. The VTR, I think as Kamal mentioned, is a sodium-cooled reactor as opposed to water-cooled. The neutron spectrum is going to be higher and the temperature of the VTR is higher. So, as we're constructing and designing VTR, if there can be things put in place to address some of these differences, in other words, if you can make it more prototypical of a light water reactor environment, maybe lower temperatures, introducing water loops, or using more of a different kind of neutron spectrum, then I think we could take advantage of answering even more questions in the light water reactor environment. But there's no question that this asset will provide support to the light water reactor community. Back to you, Katie.
Wonderful, thank you. Niko, the United States nuclear industry is competing against state-owned enterprises in Russia and China. Would you offer your perspective on how VTR can support US national security goals and possibly relationships with allies, as well as offer economic benefits and export market opportunities?
Sure, thank you, Katie. It's a great question. As you mentioned in your introductory remarks, the only testing capability that is similar to what VTR will be able to do is available in Russia, and that is a huge detriment to the companies like GE and Oklo that are looking to determine those advances for their designs, or as Randy mentioned, for the existing fleet to get that data to kind of accelerate for the existing fleet. And that's not just true here, but that's true internationally as well for other countries and other designs within those countries that are looking to develop their next generations. So this is really an opportunity for the US to lead, not just for our own nuclear industry, but globally. And the VTR can be this really key resource to build these partnerships with the US and other countries that are interested in nuclear energy to provide that low carbon electricity and energy. And those partnerships can lead then to international markets. They can open up financing, not just for the VTR, but also for commercial opportunities. And they can really leverage the technical coordination, as there are other countries that have a lot of experience with fast reactors or interest in advanced reactor designs. And with this cooperation and this collaboration, that will allow us to compete against these state-owned entities that today can offer really incredible financing packages to build abroad that the US and other countries just can't do. And Kamal mentioned, there's support from France and Japan to help the VTR with, both those countries have a lot of technical expertise with fast reactors. They have operated sodium-cooled fast reactors. And there's also another kind of good recent example is last week there was a summit between the US and South Korea. And in that readout, there was very clearly an interest in how do we develop civil nuclear energy technologies. So again, how is there an opportunity to collaborate with other countries that might be interested in the VTR? And then once the VTR is built and operating, it's also an opportunity to be a user facility. So again, US companies with these other countries, not just again, developing the VTR, but using it as an access and a user facility for their designs and their research and development goals. And so Kamal also showed the slide kind of with that collaboration from industry, the university, and the labs. And I view that as there's no reason why we can't improve that international cooperation with other countries to help, solidify those relationships. And frankly, if we build the VTR, when we build the VTR and we're working with others, it really shows that the US is serious about nuclear energy, advanced nuclear energy, these new designs and these new technologies. And so it's incumbent on the DOE and the national labs to really think about how to craft and build these relationships. Same with the administration and Congress to support these actions, where we can then use the VTR as kind of a key piece to really advancing civil nuclear technologies, advancing cooperation with our allies, and then opening up kind of that international market to commercialize and build and operate all sorts of nuclear plants. Thank you.
Thanks, Niko. So I'll remind the audience one more time that if you've got questions for our panelists, please drop those in the question box in GoToWebinar. Now I'll open it up to all of the panelists. If there's anything you'd like to comment on that you've just heard maybe from one of your colleagues, or if we want to expand on the role the VTR could play in achieving clean energy goals in the US and around the world. Just open to your thoughts.
I'll give some thoughts for possibly people that aren't nuclear engineers or with the industry that are watching the webinar, and people wonder, a fast reactor, what does that mean? Is the reactors that Randy talked about, are they slow learners, or what does fast and slow mean? So I would, the metaphor or the analogy is best to look at the airline business. It started a commercial business with propellers. It worked. My first flight was on a propeller plane that when it landed, it was at a pretty steep slope as it taxied up, and my aunt and uncle picked me up. But so that was slow. So it'd be similar to our water-cooled reactors. The fast spectrum offers that possibility of jet travel. So you can go a lot further, better reliability. And that's that transition I think that the nuclear industry needs to make, and I see Oklo doing that with their reactor. It gives us different fuel forms, different efficiencies, different things like that. So that's where I see the nuclear science and technology of fission needs to go to, is in this fast spectrum. And we sometimes get caught up in this jargon. It's hard to understand what that means, but it will definitely be a transition that will help us better utilize this gift, if you will, of the binding energy inside of an atom from the fission process. So just to kind of help in context, because we're using some fast, slow, thermal, epithermal, mix, all those sort of things. And I think in that context, that's why we need the VTR, is because we need to build that jet engine test stand, if you will, so that others can come and put different components in it, different fuels, and that's going to help benefit U.S. industry.
Thanks, Eric. Good job keeping us honest and out of our jargon mindset. Let's see, we've got a couple questions from folks just to recap, I think, some of what Kamal presented, but a little bit, maybe you can share with us how the Natrium engineering team and the VTR project team may be working together, what sorts of things are being developed in parallel or with insights from one another. And then again, the timeline for the finalization of that contract for the VTR. There's Kamal, thank you.
Was that a question to me, Katie?
Yeah, if others
Okay.
don't want to answer it, then yes, a question to you.
Well,
Timeline for issuing the contract.
Yeah, with respect to the contract for the design build contract with Bechtel National, we are down to a couple of clarifications items in terms of IP management, especially in the context that there may be some in-kind contributions coming from the team into VTR and how we manage those. But I am very comfortable that we are very close to coming to an agreement on those. So obviously it took a little longer than we anticipated getting to that contract, because part of it is we haven't done something of this magnitude for quite a while in this country. So there's a little bit of nervousness on both sides in terms of covering all the different possibilities on what might go wrong and what can be happened. So anyway, the short answer is I do believe that within a month we will be able to finalize that contract. With Natrium, we are communicating with them. The designs at the high level are very similar. One is a larger reactor producing electricity. The other one is a smaller version. On the other hand, there's a lot of technologies in there that are common. So we are looking on how we can, if Natrium takes the lead in developing those, how we can basically benefit from the work that they do in getting their demonstration up and running in 7 years, and us focusing on the experimental mission and synchronizing the schedules in such a way that not only the technologies that we can benefit from each other, but also making sure that human resources are properly shared as well, because we all know we haven't done this for quite a while, so we are limited in our human resources. We don't have a lot of experts left in the United States who know about sodium-cooled reactors. So it is, we are actively talking to Natrium team. We are hoping to achieve a memorandum of understanding between MOU, between DOE and Natrium, again, within a month or so. And as a result of that, also revising our VTR schedule so that it does take full advantage of the synergies.
Great, thank you, Kamal. So maybe open up to Caroline or Randy or anyone else who wants to share. We talked a little bit about the existing U.S. nuclear scientific and research capabilities, and a little bit about the benefits that VTR will have. How does the VTR fit into that portfolio of existing capabilities, and how might it complement facilities such as the Advanced Test Reactor, the High Flux Isotope Reactor, the TREAT Transient Test Reactor? Anything to add on that front?
I'll jump in here, Katie. Yeah, I think, well, first of all, we had unfortunately in light water reactors, we had a testing facility closure a couple years ago called Halden. Halden was a facility that was leaned on heavily by the light water reactor community to get irradiated research. So, having more test facilities be able to sort of fill in the gaps in light water reactors is important. I think light water reactors use all different types of test reactors. Fast reactor, more thermalized reactors to answer different kinds of problems. The VTR fast reactor, if we want to get to high levels of fluence, as I talked about, in short periods of time, we want to better understand what irradiation damage could do to materials. That kind of information is clearly something that the VTR could provide in a lot quicker time period. We'll still need facilities like ATR to answer questions on light water reactor research that is more applicable to prototypic light water reactor conditions, with it being water cooled and lower temperatures, different neutron spectrum. So I think having the capability, first of all, having more testing experimental facilities available for us to do research, and having different types of capabilities is important for the existing reactors.
Thanks, Randy. Does anyone else want to add on to that? If not, we can move on to a question about the importance of the experimental data in licensing, design, and operations. It can be necessary for the qualification of new materials. So how might VTR better support new material development? And I think we've heard already that it will accelerate the qualifications of those new materials, but anything else to add on the support for not only the design, but also the licensing and the operations?
So I can jump in real quick. So in my previous role before ClearPath, I was a materials engineer at the Nuclear Regulatory Commission, and a lot of what I was working on was related to these materials for the next generation, these advanced reactors that do operate at higher temperatures, higher fluences or radiation environments, and in different coolants, which can have different corrosive properties. So if you're looking at those three things, the temperatures, the radiation environments, and the coolants, and how that could corrode the materials, how all of those play together is really important when it comes to the experimental data and the licensing that can be used to validate the models that companies like GE and Oklo are using to design the reactors. So having that information is really important because it can provide that technical justification, and something that's not really widely known outside of, I think, a lot of the nuclear industry is there aren't that many materials that are qualified to operate at these higher temperatures in this irradiation environment and in these different coolants. And the VTR is a way to really broaden those options for developers so they can operate at even higher temperatures, they can operate longer, they could get a lot of those operational benefits that can really make their designs more economical. It can, again, make it higher temperatures, so you can either be more efficient, you can use your reactor to provide other products that are not just electricity. And so that's really where the VTR can provide such a key resource, is to open up those options for the developers to design kind of the next generation. So those additional operational improvements, because right now we don't have that capability, and it does make it challenging for designers because there aren't that many materials options that they can use. So that's based on my previous role, really where I see an advantage for VTR is, and that's just on the materials, not to mention the fuels or the instrumentation and controls and a lot of these other components that go into a reactor. So there really is a broad suite of components and materials that can really benefit from this testing capability.
Thanks, Niko. And maybe
add to that.
Go ahead. Go ahead, Caroline.
Oh, sorry. Yeah, I thought, Niko passed that off kind of perfectly by starting with materials and saying that doesn't even speak to the fuels. And I was thinking about speaking to the fuels. So I would say too that there's certain kinds of testing of fuels that, even if we expect to have operating reactors or fast reactors, you may not want to put your operating reactor through, and having those access to those kinds of facilities to do potentially really extreme tests or accident-like scenarios, or putting fuel in different contexts than we currently have data for, are all really useful potential uses of the facility. I'll give one kind of an example. We expect that the fuel actually can undergo really unique phenomena that actually adds to kind of inherent safety, but without actually seeing it in practice at these kind of extreme scenarios, we won't be able to rely on that in the regulatory context, right? So we have to take what is generally considered conservatisms to, in the absence of data. And I think what that leads to is, excess costs, excess conservatism, excess, belts and suspenders really can add time, require larger uncertainty bars, and maybe add operational burden or other costs and delays in absence of having that data. So I think we're really excited about having a resource like the VTR so that we can really test new next generation fuel types and even test fuel forms, and that will enable us to take less conservatisms than necessary. If you just don't have that data at all, you don't know, and so you really have to be very broad, and you can kind of optimize your operational parameters, and hopefully lower costs and timelines to getting these plants out to the public.
That's great. Thank you. Yeah, more certainty in what you're designing and how you're licensing it. So we have a question from the audience. Will the VTR design be able to accommodate higher temperature irradiation than the sodium operating temperature, since some advanced reactor designs may operate at temperatures of 600 to 1400 degrees C?
Yes. So if we look at the advanced test reactor that's currently run at Idaho National Laboratory, it operates at a temperature of X, and they have the ability, by controlling the insulation between experiments, to get the temperature that they seek. So in the case of the VTR, we have what's called extended length test assemblies that can have different coolants. We can take every coolant, I'm sorry, Randy, but water. So we don't mean to exclude you, but we did. But we can do salt, gas, sodium, lead, and those coolants then depends on how the experimenter sets it up. The outside of the experiment is going to be at round numbers 500 degrees C, but that doesn't stop inside of their experimental apparatus to go to those temperatures of 600-700 degrees C, but by the design of their experiment. So the answer is yes.
Okay, thank you. And then we have another question. Will the VTR primarily be useful for development of materials, or might it also work as a simulator for some troubleshooting for any of the advanced type reactors? I guess I don't know if they're asking more about operations or maybe just troubleshooting the types of problems that you might see come up with a advanced reactor.
So I think it looks two ways for the industry. One, it tests fuels and materials with neutrons that are on the order of 1 million electron volts. So we get to see what those interactions are. So that's the biggest one. I think the contribution that the VTR can also make is that Tom and I are working on using digital tools to get designed, and we're hoping to pass those digital tools to Oklo's and the others so they can use it. So what does that mean? The requirements management system. How do you make that so it's a database rather than a document? The building that you, or the software that you create, how do you make it more than just pretty pictures? It has dimensions, it has specifications, it has the requirements and the basis and its length. And then those other sort of tools that we could do that. So that's where I think the contribution comes from. As far as the simulator, as far as the operation goes, this reactor is not making electricity. It's a pretty simple run at 100% flow of sodium in the primary and in the secondary system, and then pull the control rods to reach criticality. So it's I don't know if the simulator, it will have one. I don't know if that'll be as much benefit as us going forward with developing tools and providing the test bed for the materials. Kamal, you came off of video. What did I misspeak on? Go ahead.
Yeah. No, you didn't misspeak about anything. You covered everything. One item we don't necessarily emphasize too much, but another goal on VTR once we get close to the completion of the operations is to be able to basically make it a test bed for data analytics that we can use for reactors in the long run. Put a lot of instruments, not necessarily just in the core, but around the reactor, collect a lot of data and start testing a lot of the artificial intelligence and data analytics, those kind of concepts. Not rely on them to operate the reactor, but basically make it a test bed and eventually couple it to a digital twin with all that data. So this is something we don't emphasize much because it's not something that we are going to be doing in the core. However, given the fact that we are designing and building a brand new reactor, it enables us to do those kind of things as well.
I'm glad Kamal brought that up. Hopefully you guys can hear me. Sorry. I'll speak really quickly. I'm glad Kamal brought up digital twinning. I was just after Eric and thinking about bringing that up as well. I don't know if this answers the person's question, but I think you really need a wealth of data to do digital twinning. We at Oklo have utilized that, and it sounds outrageous, but it's well, when you have really smart kids from MIT, but also really great computational tools and tightly coupled systems, you can really do digital twinning. But I only see that expanding even to more and more complex systems than our very first of a kind, Oklo's first of a kind. It could be other companies, other designs, and so forth, utilizing that digital twinning more and more to simulate different kinds of events and to really help with the licensing basis. So I think that's one thing. Yet another thing we're excited about is utilizing that kind of data to really firm up that kind of digital twinning simulation to help with design.
Thanks, Caroline. And was someone else going to chime in on that one as well?
Yeah, I was just going to say a couple of similar things to Caroline, where these tools are used in other industries, but not necessarily in the nuclear industry. So taking those lessons learned and applying them to the nuclear industry really presents a unique opportunity to get those improvements in the construction and even potentially in the licensing process as well, where you can use a digital twin to justify some things. So I think it's great that the VTR is approaching it this way, because it's another area that can have wide applicability to the industry.
Great, thank you. And Niko, while we've got you on the mic, we've got a question about, given the legitimate and very real need for VTR to be completed sooner rather than later, is there a solution to the congressional funding issue, which for FY21 at least could be characterized as life support? Can public-private partnerships realistically make up the difference in a timely fashion? And then maybe we'll kick to Eric for whether the 2026 startup date is still possible, or what can we realistically hope for in that flexible timeline Kamal was mentioning. So, Niko, you want to start?
Sure. Yeah, that is a great question. And the challenge is the Office of Nuclear Energy has a lot of fantastic projects at the moment. And so how DOE balances those projects is a challenge, and funding is one of those pieces. So there are potential through either appropriations or potentially through infrastructure that can kind of support programs like the Advanced Reactor Demonstration Program or the VTR, or others can provide kind of one path forward. Kind of that international support and public-private partnerships can be another piece. And going back to what Kamal said in his intro remarks, is how to leverage what's happening with Natrium through the Advanced Reactor Demonstration Program, and how that fits within the timeline of what lessons learned can you get through Natrium that can be applied to the VTR, and you can start building this timeline out for what makes sense for the broader industry and kind of this big picture approach. So I think it's going to require the new leadership in the Office of Nuclear Energy to think about how to apply, or how the VTR fits in with all of these other programs. And it's going to require, Kamal and his team to think about what lessons learned, how can they, learn from the Natrium team, and again, provide that information so there can be kind of a clear path forward for the VTR. Eric, do you have anything?
I'll answer Katie's question of yes, because Tom's going to be taking over here soon. I think it could still be built in 2026. Obviously, the funding profile has to be different. And I would just say there needs to be two words in the minds of the engineers. One is design and catalog. So what I mean by design is we have to learn how to design this digital environment faster because we're using a data set. There's no reason why we should do it slow. And that's one of the things that slows us down as an industry, is the inability to get to a final design so that you can show up on a construction site and hand it to the craft. So how do we do that? And so that's why I want to support Tom and his efforts so that we can do that better and faster. Second thing is a catalog. In my previous jobs at a startup company doing radioactive waste, if the engineer showed up with the design that they created and it wasn't in a catalog, Granger, McMaster Carr, you pick it, or Swagelok, that I said, either you change your design or submit a patent disclosure because I don't want to spend the time on it. So if it's great, we'll put a patent in. And so I think a lot of times when we start this design, we write specifications, we do those sort of things. Why not try to have that early engagement? What is in the catalog? What is in the supply chain to be able to go faster? So I would say, yes, putting pressure on Tom, but Tom and I need to get a more efficient design process so we can get a little bit faster, so we can push Kamal harder, and then use catalogs that are out there.
That's great. And I'll pick on Tom next. Is there an opportunity for the advantages of the virtual design and some of these construction tools to help accelerate? Can you explain kind of to the layperson what is virtual design and construction? What is digital twinning?
Well, it's basically trying to do and live in that world in a computer. I'll do it as simple as I can, layman's way. You're living in a computer and living in the reactor before you actually build it. And so you kind of walk around, see what head knockers might be if you're actually walking into the virtual plant. And, oh, this particular beam needs to be raised up another inch because when you're in the field, it's a little bit more challenging to try and do that. You've actually slowed the plant down construction. By having it virtually, you can do that right there on the spot and then make that adjustment before you physically get to it. And if you recall what I was saying earlier, we want to make sure the craft are turning the nut, welding the pipes and doing all that stuff and not being delayed. This virtual design and construction will help to minimize that delay. And yeah, it's going to be something we've done on other projects. It's not in the nuclear world. It's usually slow in coming around on the nuclear side of things. It took a while before nuclear even looked at 3D modeling and even using 3D structural models. I've seen that in my past. Took a long time to get to that point, but now we're doing that, and this is just the next step. I love it. I love the idea. I love what GH has done as far as putting those things together. So Eric and I are going to get really close on what he's learned and be able to transfer that into the final design and build this thing. I hope that helps.
It does. Thank you. And one more while we're on digital technology. Will the VTR be used to advance the use of digital technology such as digital safety systems? We know the current fleet is significantly analog. We know they're transitioning to digital. We know a lot of advanced reactor developers are looking to digital in the first place. Will VTR have a role in helping that, whether it's with the sensors or instrumentation, transitioning to digital technologies?
It's going to definitely support the transition to digital technologies, like Kamal talked about the different sensors and those sort of things, the data analytics. But I will disappoint some with this statement. We made a decision early in the design process that the reactor protection system was going to be analog. And because of our experience with the ESBWR, it has a great digital system, but it's tough, it's complex, it's hard to understand. And we just felt to move this project faster, let's do an analog system. There are 2 vendors in the United States that sell it. We were going to put those 2 together. So division 1 and 2 was vendor A, and division 3 and 4 was vendor B, and put those together so you get diversity in vendors and trains, and you meet all those sort of things that you need for a system. And we felt that that would help move the project a little bit faster to get operational, and then you could later add the digital controls and those sort of things. But the control system is not planned at this time to be digital. Or sorry, not the control system, the protection system.
Protection. Okay, thank
And
you.
if I may add,
go ahead, Tom.
Yeah, if I may add, Vogel, I believe, is the first plant that is starting off as full digital, and none of the other plants that we have in the U.S. are that way yet. They've converted, and much to Eric's point there, by going analog now does speed up things, and we can learn from what we're going to get out of Vogel. Another lessons learned once they're in that operational phase to see how that works, and convert as we mature the project. Maybe we'll catch it in time.
Okay, thank you. Another thing that Eric mentioned in there was where you're planning to procure some of these components from. Will the VTR be built with only US manufactured materials and components? What's the lead time to order major large components such as the reactor vessel? And would some of these SSCs be designed to ASME code, or are there code cases that apply?
So I'll go first and let Tom. So yes, we love ASME. We're going to design to those codes. And if you look at the Department of Energy, we had a code of record of the codes that we need to follow. So they include the American Nuclear Society, the Civil Society, which I've forgotten the name of, ASME. It also picks up IEEE codes. So what I want to communicate is a VTR is going to look very much like Vogel as far as the standards. There's very few that you would find that Vogel has to follow that we don't. But by and large, it will be a nuclear power plant that's going to follow the wisdom of all the different codes and standards that are out there. As far as the supply chain goes, the preference is the Buy American clause. It was in our initial proposal that we submitted to DOE about 3 years ago. When we investigated the supply chain on some of those components, some of them were a little bit harder to do. The question specifically brought up the reactor vessel. The reactor vessel, in this case, because it's 316 stainless steel, it's 2 inches thick, you roll it and you weld it, is not as difficult to make as compared to a light water reactor pressure vessel that's either 1,000 or 2,000 pounds of pressure that has to be forged and different things like that. So it's just a matter of finding that vendor that's comfortable with making rings about 30 feet in diameter, holding the dimensions, and then at some point putting all those rings together to make a vessel that's, round numbers, about 60 feet tall. So the reactor vessel isn't the long pole in the tent. There are other components that I think will be a little bit more difficult for the supply chain. Tom, what did I miss?
No, you got that right. And from our experience at Vogel, some of the things that were fabricated in the U.S., we've got to beef up that understanding and beef up the talent, because the NQA-1 programs that are needed, not all in the U.S. have kept up with it. Vogel's the only one that's been able to try and resurrect a lot of that and get things moving. So there are smaller entities that are coming along and have learned from Vogel, but now that we've got some different pieces and parts that we need for VTR, we're going to have to step that up. So that's going to be a challenge for us on the procurement side and supply chain. But that chain itself is going to really have to be investigated a lot, and we need to look at that as early as possible as we mature the design.
Okay, thank you. I think we've got time for one more question, and we may have to bring Kamal back for this one, so that's a heads up to him. What's the current status of the VTR environmental impact statement with regard to public engagement, outreach, any adjustments being made in accordance with the NEPA process?
Thanks, Katie. The current status is we opened it up to public comment period, I believe in January. That extended until March, we extended the time period for a couple of weeks per request. So by the end of March, we finished that phase. Currently, we are in the process of addressing all those comments, answering the questions, and putting together the final EIS. We are looking at publishing the final EIS sometime in summer. And then we will basically be looking for a record of decision based on that EIS on go, no go for VTR, hoping that it is a go, then the location of VTR. So we are making really good progress on the EIS, and for all accounts, it's on schedule. We have received a lot of public comments, and that was expected. It's a nuclear project after all, and there are a lot of folks who comment on that. By the nature of a nuclear project, how we are going to deal with the materials, how we are going to do the fuel fabrication, what we are going to do with the waste or the spent fuel that's going to get generated by VTR and all that. And however, we believe that right now we have the proper answers for all of those, including all the safeguards, security, and the safety aspects of it in terms of its impact. So we are very close to issuing a final EIS.
Wonderful. Thank you, Kamal. So that wraps up our panel discussion and our audience Q&A. I'll take just one moment to see if our panelists have any final thoughts or comments they'd like to provide on the VTR and its role in expanding U.S. research capabilities and achieving our clean energy goals. Caroline?
Thanks. I was just reflecting on some of the last couple questions and the possibilities. I think even as Eric and Tom talked about how certain decisions had to be made in favor of making it faster, I think that doesn't restrict how it can play a role in those things. So one of the questions was like digital instrumentation and controls. You could certainly test certain aspects of those in the reactor, although I think we would all love to see a plant, demonstrating some of the newest things that we'd like to see plants being built with, and perhaps Oklo will be one of the first, along with like Vogtle or others. But you could test sensors inside that environment. I think that's really important. I think getting back to what Eric was talking about of how do we get from, one of the other questions was about codes and standards, but how do we get to a level of safety that doesn't require a bunch of specialized codes and standards, but instead you can demonstrate that off-the-shelf components can serve the same function, or you can build plants with the safety profile that special, kind of applications of different protocol aren't even necessary. And so, if you can demonstrate in different environments that certain off-the-shelf componentry can handle the fluences and so forth in there, I think that's yet another area that Oklo is interested in testing things and showing that maybe things with 100 times lower cost can still perform the same function, or that we don't even need them to serve a safety function because of the inherent safety of so many of these new designs. Again, like Eric was talking about with PRISM, in a sense, this is both new but also quite old, right? Like decades ago, people started talking about how these kinds of plants can pave the way for the future. They're workhorse, they're compellingly strong, they have incredible safety characteristics, and I'm talking about non-LWRs as a whole, but also just nuclear in general is where we need to go. And I think some of those last few questions had me reflecting on all the different ways it can help, even if the VTR itself isn't using such and such component or such and such fuel supply and so forth, or exercising it. It can be a part of helping others to demonstrate what they need in order to use it in their next plant. So that's something we're excited about.
Thank you. Randy, do you have any parting thoughts?
Yeah, just quickly, I think that as I tried to make a case here in this discussion, is that there are the existing fleet of reactors that still have needs, and I know VTR is set up to address the future and the future advanced reactor needs. We still have 90 plus reactors, light water reactors that have gaps, material questions that we want to understand better. So I think having another experimental testing facility to address those gaps for light water reactors, as well as the future reactors, is important in the United States. I think VTR will be a great asset for both the existing reactors and the going forward future reactors.
Thank you. Niko?
Thank you, Katie. Yeah, just echoing Caroline and Randy, just the importance of the VTR as it fits into both the existing fleet and the future generation of reactor designs. The VTR can really fit a key role within the Department of Energy and the national labs testing capabilities from the list of other test reactors that you mentioned earlier, where the VTR can fit a very special and unique role for the broad support for the US industry, but also internationally. And again, it can really open up some unique partnerships and markets for cooperation and collaboration and financing, and it really can be a key tool. So the challenge is, how do we fit in the VTR and make sure we're thinking about it in that long term, and we're thinking about it how it's going to be important for the US nuclear industry for a long time. And that's where we need to think about it that way, and how the VTR can, again, help enable that next generation of reactors while still supporting the existing fleet.
Thanks, Niko. And I know we're right up against our time, but I don't want to leave Tom or Eric out. So if there's any parting remarks that you'd like to make, Tom?
When I first got onto this VTR project, it was a question of what is this? And because I've been involved with all the other retrofits and builds and stuff like that over the past. So to get onto this project, it's just exciting to hear about it, to be able to be a participant and to actually work with teams that I'm going to be leading here to advance our technology and advance the US to be the leader across the globe in this. This is exciting for me. So I'm all in on this, and I want to get this built as quick as possible. So let's go do this.
Thank you, Tom. Eric?
Let's build a VTR. It becomes another tool that we can use in our nuclear science and technology to unlock the binding energy inside of an atom that we use for fission. And at some point, we'll do fusion. So we need them both. Thank you, Katie.
Very good. Thank you all, and thank you to the members of our audience for the excellent discussion today. Clearly, the VTR is going to be a world-class facility that builds on the United States' long history of scientific research and development, and is essential to support the evaluation and testing necessary to advance today's and tomorrow's nuclear technologies. As we close, I'd like to thank Kamal Pasamemetolu for providing a thoughtful overview of the VTR project to frame the discussion. Thank you again to our panelists, Caroline Cochran, Eric Loewen, Niko McMurray, Tom Nixon, and Randy Stark for sharing their insights. And to stay up to date on the VTR program, I encourage you to visit inl.gov/VTR. The recorded webinar will also be available on the website in the coming days. Thank you again, and enjoy the rest of your day.